Okay, now that we know the various parts of the Pythagorean theorem, let's think about what the relationship or equation a squared plus b squared equals c squared is really telling us. It's telling us that if we take the lengths of the two legs, sides A and B, and square them, which means multiplying them by themselves, a squared is a times a, and b squared is b times b, and then if we add those two squared amounts together, they will equal the amount you'd get if you square the hypotenuse side, which would be c squared or c times c. That may sound a little confusing at first, so let's take a look at a special example of a right triangle that will help the Pythagorean theorem make a little more sense. This right triangle is called a 3, 4, 5 triangle because its sides have the relative lengths of 3, 4, and 5. And by relative lengths, I mean that the units of length don't really matter. The sides could be expressed in any units, inches, meters, miles, whatever. So the triangle could be of any size as long as its lengths would have the proportions 3, 4, and 5 relative to each other. Starting with the side that's 3 units long, which we'll call side A, what do we get if we square that side? Well, in arithmetic, squaring 3 means multiplying 3 times 3, which equals 9. And the geometric equivalent of squaring something actually results in a square shape. As you can see, this square contains 9 unit squares. So this red area represents the value a squared in the Pythagorean theorem. Next, let's look at the side that's 4 units long, which we'll call side B. Squaring 4 means multiplying 4 times 4, which is 16. Again, the geometric equivalent of that is a literal square that is 4 units on each side and covers a total area of 16 units. So this blue area represents b squared in the Pythagorean theorem. And finally, let's deal with the hypotenuse, or side C, which is the longest side. It's 5 units long. Squaring 5 means multiplying 5 times 5, which is 25. And the geometric equivalent is a 5 by 5 square that has an area of 25 units. So this green area represents c squared in the Pythagorean theorem. Now that you can see how the arithmetic parts of the Pythagorean theorem are related to the geometric parts of this right triangle, let's check to see if the Pythagorean theorem is really true, at least in this special case. On the arithmetic side, if you add up the amounts a squared and b squared, they really do equal c squared because 9 plus 16 equals 25. And with a little rearranging of our unit squares, you can see that the area of the squares formed by the two legs really does equal the area of the square formed by the hypotenuse. Wow, those ancient Greek dudes really were smart. Okay, but I know what some of you are thinking. That's cool and all, but why should I even care about the Pythagorean theorem? What's it good for? Well, as always, that's a good question. And the answer is, like many things in math, the Pythagorean theorem is a useful tool that can help you use what you do know to figure out what you don't know. Specifically, if you have a right triangle, but you only know how long 2 of its sides are, the Pythagorean theorem tells you how to figure out the length of the third unknown side. For example, imagine that you have a right triangle that's 2 centimeters long on this side and 3 centimeters long on this side, but we don't know how long the hypotenuse is. No problemo. The Pythagorean theorem tells us the relationship between all 3 sides of any right triangle, so we can figure it out. We know that a squared plus b squared equals c squared, so let's plug in what we do know into that equation and then solve it for what we don't know. Again, it doesn't matter which of the 2 legs is called a or b, so let's just label them like this and then substitute 2 for a and 3 for b in the Pythagorean theorem equation. That gives us an algebraic equation that has just one unknown, c. If we solve this equation for c, in other words, if we rearrange the equation so that c is all by itself on one side of the equal sign, then we'll know exactly what c is. We'll know the length of that side of the triangle. First, we need to simplify the left side of the equation since it contains the known numbers. And according to the order of operations, we need to simplify the exponents first. 2 squared is 4, and 3 squared is 9. Then, we add those results, 4 plus 9 equals 13. And we have the equation 13 equals c squared, which is the same as c squared equals 13. Then, to get c all by itself, we need to do the inverse of what's being done to it. Since it's being squared, the inverse operation is the square root, so we need to take the square root of both sides. Taking the square root of c squared just gives us c, which is what we want on this side of the equation. But it gives us a little problem on the other side, because it's not easy to figure out what the square root of 13 is. It's not a perfect square, so it's going to be a decimal, and probably an irrational number. But that's okay, because it's fine to just leave our answer as the square root of 13. Sure, you could use a calculator to get the decimal value if you really need one, but in math it's very common to just leave square roots alone unless they're easy to simplify. So the sides of this right triangle are 2 centimeters, 3 centimeters, and the square root of 13 centimeters. Let's try another example. For this right triangle,